This information here is actually from an old AP question. It says in order to monitor the population of birds, a particular species on 2 islands, the following procedure is implemented. They capture a sample of 200 birds on the island A. They attach leg bands to each of the birds and then release them. Similarly, a sample of 250 birds of the same species on island B, captured, banded, and released. Sufficient time was allowed for the birds to return to their normal routine and locations. Then subsequent samples of birds of the species of interest were taken from each island, the number of birds captured, and the number of birds with leg bands were recorded. The results are summarized. So we have 2 samples, sample A from island A and sample B from island B, in which we have 180 birds captured and 12 with bands and 220 and 35 with bands. We're going to assume that both the initial sample and the subsequent samples are regarded as random. We're going to use RStudio to run the inference procedures with the following questions. Code is shown. So if the question was, is there statistically significant evidence the proportion of birds tagged in island B is greater than 10%? Right? How do you run that? So the reason I put it that way is so that is us running a one proportion Z test. And I want you to know how to do that. So to run tests here, so prop.test, so that's a proportion test. And you simply put in the X value and the N value, so 35 and 220, and you can see the code there as well. And then you have to put in the null hypothesis. So P is equal to 0.1. You can put 0.1, I suppose, if you want. Okay. So you put X and N, the null hypothesis. Okay. And then you can put, if you don't put anything, it'll test not equal to. If you want to check greater than, you check greater than. If you want to check less than, you put less. So if I wanted to do a less than test, I'd put the word less in here like this. Okay. I don't want to do a less than test, but we could run it. Doesn't hurt. And then the reason we're putting correct equals false is if you don't do this, it modifies the variables a little bit based on the assumption that your n times p value may be less than 5. So it would fail the normal condition. And there's a test and a modifier you can use if it fails that condition to still run the test. But we want the normal procedure, so we do that. And again, this gives me a really high p-value because I did less than. So I'm going to change that to greater. And that's what we really want to test. So it says that the data is the null hypothesis. It gives you the p-value right here, 0.0017. Now it doesn't give you the test statistic, it gives you the test statistic squared. So if you want the test statistic, you simply have to square root this, 8.534. So if you ran this test in class calc, you would get the square root at 8.534. It's like 2.9, somewhere around 2.9. And then it runs a 95% confidence interval. So when you run the test, it automatically runs the interval. Now, if you want to do a test between two proportions, what you would do is you kind of do the same thing, except that instead of putting a single X value here, you put 2 of them. So you have to combine the 2 X values, which would be 12 and 35. And you have to combine the 2 Y values, which are 180 and 220. So again, we're using the C command to combine them. Hopefully you can see that on your screen. Actually, I think I'll make it a little bigger. Let's see, it's this. We don't need all of this stuff showing right now. That's not what I wanted to make smaller. There we go. So hopefully there it's down at the bottom there. I'll move it up a little bit so it's more in the middle of your screen. Yeah, I'll make this a little bigger. All right, so there it is. So we're combining the 2 X values and the 2 N values. And then in this case, we may not want to do greater than, maybe want to do less than, maybe want to do not equal to. And in this case, we just want to do not equal to. So if you leave this empty, if you don't put in greater than, less than, it'll do not equal to, and we don't need a null hypothesis here. So we're getting rid of that. So it's the X values, the N values, and then correct equals false. Okay. And it gives you the test statistic. Again, you'd have to square root this to get the actual test statistic that we used. And then the p-value of 0.004. So we do have significant evidence that these are different. Since the p-value of 0.04 is less than the significance level of 0.05 or even 0.01, we would reject the null hypothesis. The confidence interval confirms that. Okay? The confidence interval stays negative the whole time. So since the confidence interval stays negative the whole time, since the confidence interval doesn't contain 0, we can reject that these are the same. It gives you each of the sample proportions, 6.6% and 50.9%. And you can see they're already running. They're already running the confidence intervals. But if you want a different confidence interval, what you do is you just put another parameter in, and you put confidence level, and you put equals. You could put equals 0.99 if you want. And that just changes this confidence interval to 99%, whereas you see up here is 95%. So that's how you run proportions test and confidence intervals. Now, for doing the mean test, it's going to be a little bit more interesting, I think, because for running tests on means, it's going to say this right here. It says you can't actually run it with statistics, and in our calculator, we're usually running it with statistics. Like I might give you x bar and s of x, and then you plug those in to class calc. In this case, we're not doing that. We would run it with data. So instead of having the statistics, you'd have to have data. So we're going to use the data set focus. And what I'm going to do is I'm going to store all of the. So I'm going to take the focus data set, right? And then from it, I'm going to look at the major of the people, and I want to find out where that's equal to math. And we actually looked at this before, but this is how you pull just the math majors out of that data set, because the data set has 6,700 people. If we just want to isolate the math majors, you would do it this way. And then I'm also going to isolate the psychology majors. And then this would just change to psych. So now I have two separate data sets, but they're just subsets of the bigger one. That's how you get a subset of it. And this part's important because you're going to do that quite a bit in your final project, the little project you're going to do. You're gonna take the focus data set and pull parts of it and kind of compare different groups. Maybe compare math majors, psychology majors, or maybe compare people who live on campus to people who don't live on campus. Maybe compare people who have an ACT score above a certain value and people who don't. So this will allow you to find subsets of the big data set. And then what we're going to do is if we want to do a t-test, so we type in t-test just like we typed in prop test, and that's what we'd be doing because we don't necessarily believe we know the population standard deviation. So we're running a t-test, and what I'm going to do is I'm going to test to see if the math majors have if there's evidence that their GPA is greater than 3.2. So I'm going to take the math variable and I'm going to look at the GPA. So again, when I look at the math data, it's a subset of everything in the focus data set. And the focus data set is not only math majors and psych majors, but a whole bunch of information about them. What their GPA is, their high school percentile, their ACT composite score, their ACT math score, whether they live on campus or not, all sorts of stuff. And if you want to look at it, you can click on it right here. And you can see all the things up here, okay? Again, this is their composite ACT score, their math ACT score, and their English ACT score, okay? And then this is their residency status, whether they live on campus. This is their major. This is what college they're in. This is what grade or class they're in college. This is how many credits they've acquired. This is their current age, their GPA, and their high school percentile, and their gender. Okay, so all those things are available. There's 13 different variables for these 6,738 people. Okay, so we're going to look at the GPA of the math students. And again, since it's a one sample test, we need to give it a null hypothesis, mu 3.2, and then an alternative. Okay, and we want this alternative to be greater because I want to see if their GPA, if I have evidence that their math majors have a greater GPA than 3.2. And I hit enter. And you can see it runs a one sample t-test right there. Make this a little bigger. And the test statistic is 1.98. There's 124 degrees of freedom, it says. And the p-value is 0.0248. So there is evidence at the 5% level that these people who have who are math majors have a GPA higher than 3.2. Okay. It's not that different if you wanted to compare than the last test we run. These are fairly straightforward now. So now I want to maybe compare math to psych majors. And maybe I want to compare their composite ACT scores. So I'm going to say, take the math list and look at the composite ACT scores of that group. Take the psychology majors and look at their composite ACT scores. And I don't have to put anything else in. Okay. So if you leave it like that, it'll just test to see if there's evidence that they're different. And there's a lot of evidence actually. So 0.0002. So it's very strong, significant evidence the composite ACT scores of math majors and psychology majors are different. And you can see here, the mean is 24.9 for math and 23.6 for psychology. You're also seeing that it's giving the confidence interval. Okay, so if you want to change the level, you just put confidence.level, and then you put 0.90. If you want a 90% confidence interval. So when you run the test, it also gives the interval. So testing intervals run the same thing. So prop.test and t.test are the two methods or things you need to know. And those are available to you, right? If you go into here and you look at the R commands, I have them listed for you to use. So you'll see right here the inference procedures, and sorry, it's a little fuzzy, but it says prop test and t-test, and then it says chi-squared, which is where we're going to now. All right, the next one's a little bit more complicated, in that you have to, getting the data in is a little bit harder. Okay. To run a chi-squared test, we need a table of data or a matrix of data, depending on how you want to think about it. If you're running a chi-squared test, you're running a chi-squared goodness of fit test, we need a list of data. So what I have over here is, this is actually an old AP exam as well. An advertising agency in a large city is conducting a survey of adults to investigate whether there is an association between their highest level of educational achievement and primary source for news. They take a random sample of 2,500 adults in the city, and the results are below. So we're going to ask two questions. One, is the ratio of non-high school graduates to high school graduates to college graduates 1 to 4 to 2? So that's a goodness of fit test, because I'm comparing a single list, which is these numbers down here at the bottom, to a hypothesized list. Okay? And it runs a little bit different than it would run in your calculator. In the calculator, you have to put in the observed counts and the expected counts. In R, though, you put in the observed counts and the expected proportions. Okay, so just so you know, it's a little different. But you do chi-squared dot test. Okay, and then I'm going to combine the numbers. So 370, 1437, and 693. Those were the numbers of people in our survey that had not a high school diploma, a high school diploma, or a college diploma. Okay. And I just want to compare them to the proportions, which are, again, a 1 to 4 to 2 ratio would be 1/7, because there are 7 total. Oops, that's a minus sign. Don't want that. 1/7, 4/7, and 2/7. So that gives us a 1 to 4 to 2 ratio, because 1 plus 4 plus 2 is 7. So if you take them all out of 7, that's the right proportions. And you hit enter, and it runs a test for you. It says the chi-squared value is 1.146. There are 2 degrees of freedom, which of course correct, because there were 3 categories. This is good review for the AP exam. And that gives you a p-value of 0.56. So in this case, really not any evidence. It's reasonable to believe that that's the ratio, 1 to 4 to 7. Okay. Now the association test or the homogeneity test is a little bit harder because you have to make the table. It's not terribly hard. So you first, I'm going to make an education. I'm just going to call it. I'm going to just make a variable name. I'm just going to call it ed table. Call it whatever you want. I'm going to set it equal to, and we're going to use this row bind. Okay. So it's to bind rows together. And then what we do is we put in the rows the values. And you can put the values across the rows or down the columns. Rather than doing 5 rows, I'm just going to do the 3 columns to make it a little easier. So if you look at the data on the table, 49, 90, 170. Oh, that's the right one. 49, 90, 113, 41, and 77. That's the first column that's right here where it says high school graduate. I can't highlight just that column, but it's right here. And then you put a comma and you bind it with the next one. So C to combine these numbers. So 205, 170, 496, 401, 165, and that's the end. And then finally the last one, which is the last column, 188, 75, 147, 245, 38, and 693. No, that's not right. Too many. I went too many again. Okay, so that's it. You can't, don't put in the margins. That's a mistake sometimes people make when they're running chi-squared tests. They put the margins in, and that's incorrect. You just want the data in the two-way table, so none of the total. Now I hit enter, and all it does is it makes the table. Okay, so now I gotta run the test and actually store that. It's easy to store that into a variable. So now I'm going to do chi-squared test, and I do it on the table that I made. So you make the table, and then you run the chi-squared test on that table. So let's see what. Oh, there we go. And you can see the information's there. So a chi-squared value of 1 point. Oh, that's not right. Where did it go? How come I must not hit enter? Oh shoot! Sorry. I'll do that again. Okay, so there it is. So the chi-squared test statistic is 217, 8 degrees of freedom, and a p-value basically 0. So there's a whole ton of evidence, okay, that these things, there's an association between these things. But if you want any other information, like the observed or the expected counts or the components, you actually have to store the results of the test into a variable. Okay. I'm just going to call it ed chi, education chi. And then what you can do is you can take that variable and you can say, I would like the expected values. And that gives you all the expected counts. So there's expected counts in all of those cells. Or if you want the components, I should delete this. They're actually the residuals squared. You square the residuals. Oops, so those are the components, and this would be important in this case because we'd say, okay, well, what really stands out? Okay, well, what really stands out here would be the number of non-high school graduates that get their news from local television. That one's 32. That's really big. And then this one, which is the number of college graduates that get their information from newspaper. Okay. So the college graduates that get the information from newspaper is way bigger than we expected it to be. And the high school graduates that get the information from television is also way bigger than we expected it to be. So those are the ones that would stand out. And that would give you kind of an important information, and you want to talk about it if you were giving a write-up on this. All right, one last thing, and that's regression analysis. Now, there's not going to be, I actually didn't find any really good regression, but it'll be kind of an interesting conversation. So there are 4 things: plotting, finding the correlation between the variables, so those with the plotting, and then looking at the linear model and getting the regression summary. So I'm just going to plot, And I'm going to use this math variable that I had before. And I'm going to look at the high school percentage, high school percentile, and I'm going to plot that against their composite ACT score. Because I would assume that if your high school percentile, like if your ranking in high school is higher, you should have a higher ACT score. That would be my assumption. And you can see actually I've already plotted it earlier, but it's over here. And it doesn't look that great, right? Like there's some people up here that have high school percentiles close to 100 and have ACT scores of near 21. So that's not really all that positive. And then there's some people who have ACT scores of 30 that have high school percentiles in the 80 percentile range. So it doesn't look like there's a very strong relationship. Well, we can find out what that relationship is. And I just, instead of saying plot, I'd say core. That would give me the correlation. So 0.35. So very weak positive relationship. It is positive, but it's very weak. But this is interesting. Even though the correlation is not very strong, that doesn't mean it's not statistically significant, which is something we talked about in chapter 12. You might have a really weak correlation, but it still could be significant. We can explore that. And to do that, you need to create a linear model. So I'm going to say LM, that stands for linear model. And to make a linear model, it's a little, it's not confusing, but you just have to remember that you put in the response variable first. And then you put a tilde, and I'm saying I'm creating the model with this variable, and I'm saying it's responding to, or this explanatory variable. So in this case, high school percentile. So that creates the model, which again doesn't help us much, but then to see it, we make a summary of it. And you don't have to call it model, I just chose the word model because it seemed appropriate. I'm gonna scroll down a little bit so you can see it better. So it gives you the model. It says we're doing a linear model of this information. It gives you the estimate of the intercept. So the y-intercept is 16. So we would assume that someone who had a high school percentile of around 0 would have an ACT score of around 16. And it gives you the slope, 0.098. So for every 1 increase in your high school percentile, we would predict that your ACT score would go up by about 1/10 of a point. That's what we would say, something like that. It gives you the standard error of the residuals, so 3.283. So when you go to predict their ACT score, you're going to be usually within about 3.283. So it's, you're not making very good predictions. It gives you the R-squared value, which we knew was going to be pretty low. But then if you look at, is it significant? It is, because if you look at this slope here, 0.908, and you look at the test statistic, it's 4.19, and that has a p-value of basically 0. So although there's not a strong relationship, it is significant. It is true that when people do better in high school in their grades and their percentile, they do better on the ACT. There's evidence of that relationship. All right. So that was our overview of regression, chi-squared, means, and proportion procedures.